All right, let's get started. Thank you for coming to this tutorial. This is about scalable deep learning with Microsoft Cognitive Toolkit, also known as CNTK. Before we started, I would like to show of hand, how many of you are familiar with deep learning and all the basics? Okay, so I see most of you are actually already been playing with deep learning. So in case some of you haven't know much about deep learning, there is a edX course that's created by one of the co-speakers today, Sayan, and a few others on edX called Deep Learning Explained. And that's like a 40-hour course, and you can go there and take a look. So this is our agenda. We'll give a brief introduction. What is CNTK? Why use CNTK? And then we will go through some basic operations in CNTK, as well as talking about a number of applications. So this includes image applications, video applications, and then we'll talk about parallel training, how easy it is in CNTK to enable parallel training across multiple GPUs and multiple machines. And then we'll talk about how can you port models from a cafe. And the last topic would be doing reinforcement learning in a simulated environment. And then conclusion and Q&A. So let's start. So what is CNTK or Cognitive Toolkit? This is Microsoft's open source deep learning toolkit. Actually, I got a lot of questions. People asking me, is this open source or not? So CNTK was originally developed by Microsoft speech research team in 2012. I believe many of you probably have heard that the deep learning passion in the industry actually really starts at Microsoft Research, where our speech recognition group first ever basically showed that deep learning is performs really well in speech recognition applications, and that was published in ICASP. And after that, the second year, Jeff Hinton's team showed a really good result on ImageNet, and that's kind of the whole field really went up. So we were one of the first to really start and enable deep learning in industry settings. In April 2015, CNTK was open sourced on Coplex, and that was with a relatively restrictive license. So in January 2016, since then we have moved it to GitHub, and now it is under MIT license, which is one of the most open license you can get, and it is renamed to Cognitive Toolkit. We have community contributions from MIT, Stanford, NVIDIA, and many others. The toolkit currently runs about 80% of Microsoft's internal deep learning workload. Also about 70 to 80% of the Microsoft internal employees use CNTK. Microsoft kind of run the deep learning toolkit slightly different, where we do not have a top-down kind of enforcement that everybody has to use a single toolkit. So this is completely voluntary when they see the benefit of using CNTK, particularly when it scales, particularly when in the application of recurrent neural networks. It is a first class on both Linux and Windows, and it has Docker support. In June 2017, we released version 2.0, and that includes a beta version of a Keras backend support. We also have Java support for evaluation on Spark clouds. And then we have shipped a fast binarized evaluation for model compression. So let me talk a bit about some of the advantages of CNTK. Now, we often hear that every toolkit kind of say they are the fastest toolkit. So this is a study actually done by a third party, completely independent. It's a study from Hong Kong BU. So they basically compared 5 different toolkits, and you can see that basically CNTK wins across the board. We're fastest on fully connected networks, AlexNet, ResNet, and particularly I would like to call out LSTMs. And you can see that for recurrent networks, we are easily 5 to 10x faster than any other toolkits out there. So if your application ever uses LSTMs or something, it can definitely help you a lot in speed up your iterations. CNTK also, because it came from the speech group, it's kind of the very first toolkit to be made production ready. So because Microsoft internal speech groups in the production environment started using CNTK a long, long time ago. So back in December 2015, you can see from this figure that CNTK was already able to do parallel training. And you can see this is, at that time, GPUs are not that very strong yet, but, and communication across GPUs are difficult to achieve. And we were able to invent new algorithms such like 1-bit SGD to be able to allow almost linear scaling across different tasks, across different machines, while all the other toolkits are kind of not able to do anything across more than a couple GPUs. We work very closely with NVIDIA, so this is a collaboration that during this year's GTC, NVIDIA demonstrated that CNTK, I guess the first toolkit that is running with Nickel 2.0, that is NVIDIA's new communication protocol. It was able to basically doing gradient aggregation across multiple GPUs as well as multiple machines. So you can see basically the number of hours drops almost linearly with respect to the number of GPUs being tested. We also were ever tested on, this is a Cray Supercomputer. I think we have tested CNTK on over 1,000 NVIDIA Tesla P100 GPUs. And so basically it can scale up to very, very large scale. Now let me mention a few other benefits. I think some of them I will add more details in the later slides. So the first one is accuracy. Every example that we published in the CNTK toolkit has been verified, and some of them gone through very, very lengthy process. Just to give you an example, the ResNet network originally was published on Caffe. It took us almost 3 months to get it parity, and in the end, we actually achieved a better performance than any other toolkit reported. The Inception v3 model, which is originally from TensorFlow, and if you go use their script published, you would have some difficulty getting the same numbers as what their paper reported. And our researchers spent a lot of time figuring out the right way to do data pre-processing and all the details. And our Inception v3, the published example, was able to achieve better performance better accuracy than the paper published as well. And the second point is that CNTK has been designed from the very beginning as a C++ API. So it's mostly implemented in C++ for both training and test. And as a result, CNTK can run really fast because there's no performance penalty when you're running through data, for example, in the Python API. We also, on top of it, design a very thin wrapper it's both a low-level and a high-level Python API, which is actually very easy to use. And we will show you a lot of examples during this tutorial. And the next point being CNTK are very extensible. User can define their own functions and learners in pure Python or C++. And the last but not least, CNTK has built-in readers. Now, when we talk about distributed training, many of you probably didn't realize that the way to suck in all the data into GPU is extremely critical. It can easily make a difference of 2 to 3x speed up if you have an efficient reader. So CNTK offers out-of-box readers that can allow distributed and highly efficient built-in data reading data, and it handles basically all the randomization, everything, making sure that everything can be run correctly. In the 2.0 release, we also supported the Keras. So if you switch your backend from TensorFlow or Sayan to CNTK, you will realize your LSTMs will be easily 2 to 3x faster. And I shall mention that because Keras takes in NumPy arrays as data, so there's some loss of efficiency when you run LSTMs on Keras. If you run the native CNTK code, it will be easily 5 to 10x faster. We also have a binary evaluation, which we will not talk too much today, but we basically have a demo that can run CNTK AlexNet for about 20 frames per second on a Raspberry Pi. And the last point is that in this particular case, CNTK is a completely equal version between what the internal product group use, as well as compared with the thing that we published on GitHub. So it's same tool that's used by internal Microsoft product teams. So let me go a little deeper and tell you a little about what is CNTK. So CNTK expresses arbitrary neural networks by composing simple building blocks into complex computational networks. So let's use a very, very simple example. Let's say you want to write a 2 hidden layer feedforward neural network, right? So in this particular case, you have a W1 times X plus B1. That's a 1 linear layer with a nonlinearity. Then you have H2 add on top of that, and then you have a softmax on top. So you got an X input is from a m-dimensional vector. And now you also define a one-hot vector label Y, and you can define the loss function as the cross-entropy loss, right? So this is math equations. So converting to Python scripts, this is how you would write it, right? So H1 is sigmoid of X times W1. This is a vector times a matrix plus B1. H2 is the same thing, and then you have softmax, and then you have cross-entropy. So once you write this Python code, CNTK will compile this Python code into a back-end graph. So in this case, all the weights, all the bias is going to be edges, edge kind of inputs to some nodes, where these nodes are essentially functions that process these inputs and weights. The original input X at the bottom was fed into the whole graph, and then it basically runs through the whole graph and then obtain the final output. So I already mentioned nodes are functions, edges are values, and the main reason, of course, to have such a graph is to do automatic differentiation. So CNTK does automatic differentiation, that you don't need to really worry about how you compute derivatives of the loss inside all the nodes in the graph. So once that graph is built, CNTK basically compiles then the graph into an execution thing, and then it executes. And that's basically a very efficient way of running this graph. The graph is editable, it's clonable, it's kind of like Lego, where you allow CNTK to support a wide range of networks and applications. So I would like to also mention 3 very unique features in CNTK. They are basically symbolic loops over sequences, and then how do CNTK turn parallel programming through mini-batching. This is an effective way of packing the data, making it really fast. And then we'll mention a few unique parallel training algorithms like 1-bit SGD or block momentum. So let's go back to the very simple example of 2-layer network, feedforward network. And let's say, let's change this example to a recurrent one. So what you do is essentially adding a time axis. So H1, the first output, H1t, is now not only a function of the input xt, but also a function of the previous state, H1t minus 1, right? So, so on the left, you see the math equations, and on the right, you basically see how you translate these math equations into Python code in CNTK. So it's notice here, past value is a special operation. It's not a keyword, but it's very intuitive. You just say this is my previous value of H1. You can also write past value of H1. That will be 2 steps ahead. With that Python code, CNTK basically take this and convert it into a new graph. So this graph is different from any other toolkits. If you notice all the red nodes we have here, this is a symbolic loop. So essentially, these loops are actually part of the representation of the CNTK graph, which is not seen in any other toolkits. And during execution time, CNTK automatically unrolls these circles. And of course, first you need to detect these circles with a tangents algorithm, and then it unrolls and runs it extremely efficiently. And this is also composable. You know, you can take these circles and compose with other stuff. The second unique feature in CNTK is called the batching. So here's the idea. So typically, in most of the other toolkits, if you want to handle sequences, and we know that for sequences like speech or language, you usually have different lengths, right? So there are sequences that may be 20 words long. There are sequences that's 5 words long. And the most kind of straightforward way when you do batching is basically put them side by side, and then you start run the graph on these data. The issue with this approach is then that the sequence 2 in this particular case is very short. So once sequence 2 finish, the GPU basically will be waiting there doing nothing, right? So this is very inefficient. So in other toolkits, they will ask you to manually do batching, which means you want to manually align similar length sequences, put them in the same batch, and then you train it. Of course, that kind of compensates a little bit about the efficiency, but then it also screws up the randomization, because now you are kind of manually doing the randomization, which actually affects the final accuracy. So in CNTK, what we do is this following trick, which is basically saying we look at sequence 2 and sequence 3, and we say these two, even you add their lengths together, it's shorter than sequence 1. So let's just put sequence 3 behind sequence 2. Right? So that's scheduled to the same slot, and then the computation comes all for free. Right? So CNTK does this packing completely automatically. You have, in this particular case, 7 sequences packed together into 4 kind of sample sequences. And this is done completely transparently. So user completely have no aware this is happening. But during the recurrent computation, CNTK unrolls and handles the sequence boundaries. And if there's no recurrent, then CNTK will just do the parallel computation. And during the inference, when you need to do sequence reductions, then you also need to make sure that these sequences are masked properly, so that the condition on the previous time stamp will not propagate from, in this case, say, sequence 2 to sequence 3. So you have to handle the boundary very, very carefully. This looks very simple idea, but actually it's almost 30–40% of the code in CNTK. That it's a very complicated thing, but it does improve the efficiency of CNTK of recurrent network a lot. And the third unique feature I would like to mention is data parallel training. So this is kind of this slide showed a very naive way of doing data parallelism. So the idea is you take a mini batch of data, and then you distribute the data into multiple nodes. This is a data parallelism. And then you compute the gradient, and then you have an all-reduce operation to aggregate all the gradients. And then after you do the all-reduce, you kind of send all the gradient back into all the nodes. Of course, this is highly inefficient. So there's a better way of doing this. So in this particular case, essentially, you kind of cut this model into 3 chunks, right? So each node now handle one of the chunk, right? So node 2 will send its first piece of the model into node 1. Node 3 does the same, and node 1 takes care of aggregating the first piece of the model, and then so on and so forth for node 2 and node 3. And then once that's done, node 1 is responsible to send the first piece back to node 2 and node 3. And this is a very effective way of reducing the amount of communication happening during distributed training. It's a known algorithm, well-known algorithm, typically referred as a ring algorithm. It's O1 with respect to K, where K is the total number of nodes, how many GPUs you have when you want to do distributed training. So this is O1, but is this good enough? In the older days, when the speech recognition team just started doing deep learning, most of the networks are densely connected networks. So that means, from layer to layer, it's basically a matrix multiplication plus a bias. So the computation is actually not that expensive. However, because it's dense matrices, so the communication cost is actually very high. Just to give you an example, if we have a DNN of a many batch size 1024, and you say I have a model that's 160 million model parameters, and you can see that computation per mini batch is likely to be around 1/7 of a second for a particular GPU we tested. And the communication, however, takes about 1/9 of a second for transmitting essentially 640 megabyte data over 6 gigabit byte per second pipeline. So you cannot even parallelize to 2 GPUs because the communication cost already dominates. Now, of course, there has been plenty of work doing it asynchronously, and the idea being that it helps for reducing latency and jitter, but the amount of data that needs to be transmitted is still large, so it does not change the problem fundamentally. So CNTK has a number of tricks, which we will have a special section later during this tutorial. So essentially, the idea being that how can we reduce the communication? So one idea is to basically communicate less. So that's the algorithm called one-bit SGD. And the second idea being to communicate less often. So we have 2 approaches. One is automatic mini-batch sizing, and the second one is called block momentum. And this is, I believe, the last slide for introduction. CNTK, so once you train a CNTK model, how do you evaluate that model? So CNTK currently have multiple language support. It supports C, C++, C#, Python, Java, etc. And in CNTK's case, we're mostly focused on directly integrating CNTK evaluation into user function applications. So we can do parallel evaluation of multiple requests with limited memory overhead. Now, with this as an introduction, I'll hand over to Sayan. I will tell you more about some basics of the CNTK toolkit.
Thanks, Cha. So before I walk you through the basics, because many of you are quite familiar, just wanted to get a sense, like how many of you were in the MXNet session in the morning today? Okay, all right. So that tutorial covered a lot of the basics. So I am building on top of it, and we'll just show you a quick one on how to install CNTK. So you can just do a pip install from a URL. Oops. And from a URL, and you can choose whether, depending on a platform, Windows or Linux, and then we offer different options. If you just want to do the Python only, you can just do pip install. The details are inside these links, which you can find at the URL below. And then we also offer you script-driven installation that will pre-install all the prerequisites and environment stuff, just convenience stuff for you. And for those who are actually involved or want to be get into the code, they can go for the manual installation, which is also script driven, but you can do all these steps yourself if you choose to do so. The scripts just help you with some time savings. We recommend people coming to CNTK. How many of you are new to CNTK? Okay, great, perfect. So people coming to the toolkit start with these tutorials that are comes bundled with the package, with the software package, and you can see there are broken into 100 series 101, and from here, this covers pretty much the basics of the feed-forward dense networks, MLP networks, then basics of convolutions, basics of RNNs, LSTMs, and then it goes into the 200 series, similar to a university course, where we talk about, more like deep convolutional networks. There's some language understanding related tutorials, reinforcement learning, sequence to sequence, GANs, neo-artistic styles. Some of it you will see in today's tutorial, where we will walk you through these advanced set of recipes. We will assume that the 100 series are well under your belt, even though you haven't gone through them. And if you need further assistance, you can use the edX course that Shah pointed out at an early stage. These tutorials you don't need to install. For these tutorials, you don't need to install on your own machine. You can go to the tutorials on the Azure site. It's free. All you need is a Hotmail or an Outlook ID, and anybody in the world can run these tutorials at their convenience. Yeah, it comes at a price that if you're going to run the convolution net, it might require you a lot of cup of coffees. So, or take a long nap, set the mini batch size to small things like that. But from a learning experience, you kind of get it. These are all CPU-based machines. So if you want, we do really recommend that you try to run CNTK on the GPUs for bigger image loads, which I'll be talking shortly. Besides the tutorials, at our GitHub site, we have published a rich set of examples. Some of it you will get to see today. And then we also have manuals where we, as a team, we have, over a period of time, collected some knowledge that helps us train these models better. As Cha was mentioning, that getting a model to just work is relatively easy, but to get the performance out of it and to run it more efficiently and debug them, there's a lot of good knowledge that is encapsulated in these manuals. And these are all working notebooks. So this is our cognitive toolkit site, where you can find a whole set of further information about the details and the APIs and documentation. The Python APIs are listed here. And one thing I would like to mention is that our development framework is completely open. So if you go to our GitHub site, you would be able to see what all we worked in this month's iteration. And we publish our iteration plan for the next month. And people have commented on it, and we have changed our plans based on people's participation on the so let me see if I have that loaded up somewhere. Yep. So this was the iteration plan for July, and we published it, and there's been a whole lot of activities from the community. So really appreciate the community's engagement. If you want to use the toolkit, give us the feedback. We listen to you in a super active manner. All right, with that, let me walk you through the workflow for CNTK. All these components, the reader, the network, and the trainer, these are super important for building any deep learning network. For readers, like Shah mentioned, that out of the box, we package many of the readers that scale very efficiently across large data sets. So if you are to scale your model, a lot of the tutorials that you see online from different toolkits will allow you to do quick data sets, small data sets, Cypher, MNIST, maybe AlexNet, small data sets that you can quickly fit in the data in a computer and build your example quickly. But when you actually have to scale up to a larger data set, as many of our customers do, you run into the issue of randomization being one of the basic ones. You can do all of the stuff that we do internally with the toolkit yourself, but you will be spending time in debugging and developing it. So let me show you the workflow in terms of the code. I'll start with the reader, and then I'll walk you through the network and the trainer components and highlight some salient features of the toolkit. So here we create a reader. Then you can create the model function. We'll talk about the criterion function. This was the cross entropy loss and the error of the error that you can calculate during training, classification error, I mean. Then you can run the trainer with the reader, you pass in the reader and a model that the model function creates. And then you run once your model is trained, then you can evaluate the model in the context of another reader that may read test data. So here you create the model, you create the reader, and here by setting this flag, as simple as setting this flag is training equals to true, randomization across petabytes of data in a distributed file system gets enabled for you. So many of the things may look very simple, and if you think this is pseudocode, some of it is, I'll try to identify wherever it is, but in all practical purposes, that's all you need to do. So it's simple. We try you to focus on building bigger data sets and working on the networks and taking the whole community of deep learning to the next level, and instead of worrying about the engineering components, which we package with this toolkit. So you have the train, and then in this case, if you see the reader, we are not randomizing. This is for evaluation purposes, and we don't want to randomize there. So that's one of the efficiency aspects of the toolkit. So what you do is you prepare the data, you configure the reader, the network, and this can be done in Python. We also have the C++ API that is available to, is unique to CNTK in many sense. Many toolkits do call into the C++ layer, but we also expose that for you to consume. Here you can call Python and your mycntk.py. Inside it, you may be curious what's going on the reader. So here, if you see there's a deserializer, we have the image deserializer here, and there are details in the documentation. I won't spend time there, but then you can set this flag to be true, and then you can repeat or resample through the data as conveniently as you want. But the point to be noted here is this part. So imagine that you want to train a reasonably good image network. You would actually spend a lot of time transforming the data, probably creating some mappings of those transformed data, cropping, jitters, noise, whatnot. Here, you can just add transforms to the image deserializer, and it will automatically do those transformations. In this case, it's a crop type of random with a ratio of 0.8, and you have a jitter type. You are doing a scaling here, things like that. So there are other functions that we support that's also available in our documentation. The bottom line is we try to take away that burden so that you can just specify these transforms, and the reader automatically will randomly keep doing this for your data set that you want to train on. So this allows very scalable, automatic, on-the-fly randomization for large data sets. And you can also compose different readers, like text and image together. In that manual section that I was alluding to in my previous slide, you could see how you could do that. So just a quick recap. Here is a multi-layer perceptron with 2 hidden layers and an output layer that you could do for an MNIST. And the model, if you are using the CNTK layers library, which is very similar to KRS's library, except that this one directly calls into a C++ layer and is very, very performant. Yeah, it looks very simple, as simple as the figure looks like, probably even simpler than the figure. You can see that it has the first dense layer. You pass it as the input to the next one, and so on and so forth, and finally you get the model out. Then you have the loss function. We support several standard loss functions, and you can pass the model output here, compare it with the labels, and then you can minimize the loss. I'll show you the entire workflow shortly. In convolutional network, you don't flatten the image. You keep the spatial correlations. I don't want to spend time talking about convolutions here. So again, it's very simple. A simple convolutional network is pretty much 5 lines of code here that you would, from the modeling perspective, for the simple ConvNet is very compactly represented. You'll see later on in the presentation as we talk through the advanced networks, how these type of constructs, which are made available to you through CNTK's layers library, can make even more deeper networks like ResNet, which has ResNet 152 has 152 layers, can really help. You can write very concise code, express yourself clearly, spare yourself from spending debugging the network. Sequences are becoming increasingly common, as you could see from yesterday's talk by the speaker, that when you see the primate's brain, maybe the next frontier is to understand how recurrences are handled in our interpretation of images. So here is a quick intro to sequences. We'll talk a lot more about it in the slides later on, but here is a set of word tokens in a sentence, and you want to classify them. This could be also image frames in a video, and what you want to do is the classification of a word is predicated on the word before that. So that's how the recurrence schema is built in, where you want the previous states to influence the prediction of a later state. In this case, I have shown only recurrence in the forward direction. Later on, you'll see how conveniently and easily you can do this in any direction. And CNTK has some very nice frameworks that allows you to write the code equally concisely as it was for the fully connected non-recurrent networks or the convolutional networks, just the feed-forward ones. It does support applications where you combine images with text. So in this case, you have the image captioning example where you take one input, the image, and you can generate the corresponding outputs, the captions. We have a couple of slides talking about how you could possibly do that in CNTK. So here, this is what if you wanted to classify those text tokens into words, what you would think of that, how can I classify one token into its corresponding classes? Right? That's how you start thinking about it. So you have take one token in this case, or one image frame if you might. In case of text, it's a one-hot encoding of the word in your vocabulary. In this case, the length of the vocabulary is 943. You embed it into whatever space you want to choose. In this case, it's a 150-dimensional vector. You run the recurrence, and then you cast it through, project it to a dense layer into the corresponding number of labels. In this case, it's 129. So this is exactly the model that for classification of text looks like. This is the code. Because in many toolkits, you'll do looping through the sequence axis. We take care, as Shah explained shortly before this slide, that we take care of loop unrolling automatically, so you don't have to worry about it. So there are many learners that are built in. So all the popular ones are called out here. What you can do here is you can specify the learning rate and momentum schedule. So what you mean by that is that here you can see that during the different epochs of data that we want to process, we want to pass the learning rate to be 0.05 initially, and then you gradually lower it down. Similarly, you can do you can do momentum scheduling for those learners that take momentum. And additionally, you can also do mini batch size schedule. So by specifying the schedule in this way, you can have a full control over how you want to use your data as you learn and fine-tune your model. So overall training framework here, and I chose the sequence one because it's the most general way of the data can be passed in. Obviously, in most of the image cases, if you think this is the pixels of an image, and most of the times the images are the same size, then this matrix, this data set, this mini batch would be a fully filled mini batch. But if imagine these are videos of different length or tokens in a word that are of different length, the sentences are of different length, you as a user just submit. You sample from this training set, you just submit those, you sample randomly and submit these 96 samples. Internally, all that thing that Shah just explained to you shortly will happen. And what we will do is, In this case, each of these blocks are one-hot encodings of the vocabulary word and the corresponding label, and that's going to be your model. That's literally going to be your model. You'll do cross entropy with softmax, where you'll pass the model and the corresponding Y, which is your one-hot encoded label, and then you can optionally also measure the error that you can, the classification error produced by your network. You can choose your learner and then call the trainer. That's pretty much. This is the tutorial CNTK 202. If you want to get a glimpse of it, what it means in terms of the automatic unrolling, because that might be a new concept for you, take a look at it. You'll find it pretty convenient way of expressing yourself and dealing with sequences. You can do things a lot faster. Now that you have a sense of how CNTK works, you created your Python recipe with the reader, with the trainer, and the components within the trainer. You want to now scale it out across multiple GPUs. If you're in the session previously, you could see that how many people do that. You have to do gradient aggregation, and you have to do a lot of code around it. In our case, because we have distributed readers and many other efficiencies that are coming along with the way we aggregate gradients, you can just call this MPI exec. You specify the number of processors here, and then you have the hosts. You provide the IP addresses. Obviously, you have to make sure those hosts are configured. They have installed CNTK. They are doing the right things themselves. And then you pass on your same myCNTK script. Okay? And the whole recipe, whatever you have, will scale up. Now, so far I've talked about pre-canned operations, but you can also provide custom layers with built-in ops. So in this case, these are some of the operations that you can write in pure Python, and it will be using the CNTK primitives, and you can write your own operations. Or if you want to really want to implement your own functions that are not built on CNTK primitives, you can define the forward, backward, and the infer outputs functions, and that would be your custom layer in Python. You can also have custom learners that you can try out with this toolkit, plug it in. You should be able to reap the benefits of what the toolkit has in terms of the engineering gains that we just explained. And here is the manual that talks about how to use learners. If you go to that directory under the master and manual, you'll see many other such nuggets of information which will help you scale and do deep learning in a very effective and efficient manner. With that, I'm going to pass it on to Emad, who's going to walk you through some very cool image networks.
Hi, everybody. So we'll go through a lot of image and video-based algorithms, and we'll see how we'll implement them in CNTK. So first of all, let's start with one of the top three feedforward network that won at some point in time ImageNet, and people use them for pre-training. And we'll see how we'll implement each one of those in CNTK using the high-level API. So let's start with VGG. If you look at the right here, this is the VGG 16 network. It's from Oxford University. VGG usually it have number next to it, which indicates the number of layer. So VGG 16 means there is 16 layer. There is VGG 19 and 13 and other version of VGG. It's a very easy network. Most people use it because it's easy to modify and tailor to your own application. It is composed of a block convolution pooling, multiple convolution pooling, and this block keep repeating until you reach the dense layer. The code on the left is the CNTK high-level API. As Shah said at the beginning, we have two types of API. We have low-level Python API, and we have high-level Python API, which make coding any network much more easier. So here we define the default option. Those default options are parameter to each of the API, so you don't need to write them explicitly. And then this, if you see this network, each layer reads the output of the previous layer. So you can use the sequential API to stack all the layer to stack all the layer over each other. Now we said those blocks get repeated. So in our layer API, we have a for function that can repeat the block behind it. If you see range 2 mean repeat this block 2 times. But if you look at the VGG, you will see the first block convolution have a feature of size 64. The second block have of size 128. So how we deal with that? We specify lambda with I indices. This I indices will be 0 the first time and 1 the second time because we have range of 2. And here we specify all the future size of the convolution as a list in Python. And this I will select 64 for the first one and 128 for the second one. The second block is the same, but we repeat this block 3 times. Then after that, we have the dense layer and then the dense. So this network in CNTK API expand to the full VGG16 network, and you can write it in easy to read and in concise manner. Next, we'll go residual network. Residual network was published by Microsoft MSRA and won ImageNet in 2015. One of the idea of residual network is the skip connection that you see it here. The reason for that, they said, if you have a network with n layer and you give it and it produces a performance, for example, P1, if you increase the number of layers, theoretically, you shouldn't get worse, because worst case scenario, it will learn identity. But in practice, that's difficult. Once you increase the number of network, it's difficult to train, and usually it gets worse. So the idea of this skip connector connection, or the residual, as called in the paper, it make it easy to learn the identity. So you can stack deep network on each other, and worst case scenario, you will not get worse, but you can get a little better. And the network that won ImageNet, it was 152 layer. It was one of the first time that we can train network as large as 152 layer without any problem. Another advantage for this skip connector, if you guys familiar with the vanishing gradient problem, when you do back propagation, each time you move back to the layer, the gradient gets smaller and smaller because of the multiplication factor. So the advantage and the problem that when it reaches the beginning of the network, it's already very small and it does not affect the network at all. So having those skip connection, the gradient flow without any reduction. So that helps the gradient to flow back to the beginning of the network. So how we can implement that in CNTK? As you see here in ResNet block, we define a convolution net, another one, and then you simply add the output of C2 to the input, and this will give you this skip connection. The convolution underscore B, it's simply convolution with batch normalization, so there is nothing special about it. The other network, it's similar, but it reduces the dimension. So it have one-on-one convolution with a stride of 2, and you add it at the input. So so the one in the drawing, it keeps the dimension the same, input 64, output 64. The ResNet basic include it just half the dimension. And here, a small ResNet network, we simply define a helper function that repeats the basic block, and we simply create layer by layer those block, and then we end up with global average pooling and dense layer. So next, let's go in Inception Network, which was published by Google. They have multiple versions of Inception Network. Each of those have a different, most Inception network are composed of a bunch of blocks that you connect them together, and each block it's a little more complicated than previous networks. So here, one of the block, we will not show the entire Inception network because it won't fit here, but we'll show one of the block, and all blocks are similar with some minor variation for specific reason. So this is one of the block of Inception network. You have here the input. You first reduce the size of the input by one convolution, and then you do 3 by 3 convolution, and here 5 by 5, then you can concatenate all those branches together. There is various reasons, as mentioned in the paper, why this is helpful. One of the reasons that you reduce the computation cost. One of the goal of Inception Network is to run into mobile devices. So how to implement that into CNTK? You simply define all those branches separately, and simply splice all of them together. Splice, it's concatenate, simply. It concatenate all the branches together. And this one, it defines this entire block. And all other inception blocks are very similar with very minor variation. So you can define each of those blocks and concatenate together. Both VGG, ResNet, and Inception, we have the full implementation in our example with the pre-trained model trained on CNTK from scratch and match the paper, and even some example beat the paper number as Shah mentioned. And the examples that we checked in CNTK, you can run them on your own computer and you will get the same number. So this is the one that we spend a lot of time to make sure they match exactly the number published in the paper. So now that we saw some of the basic how to implement a feedforward network and some of the well-known network how to implement them in CNTK, let's look at some a practical application. Emotion recognition. We'll use emotion recognition from facial expression or appearance. The goal of this one, or the takeaway, will show you how to implement a custom loss function. And this emotion recognition, it uses a version of VGG network that is tailored or changed to adapt it to emotion. But the thing that new here is that we need to implement a custom loss function, and we'll see why. So emotion recognition recognize, for this paper, we recognize 8 emotions from each facial expression. The data set we have for each face, we have 8 emotions, the probability of each of the emotions. So we don't have one target like most image data set. We have, for each image, we have a probability for each of the 8 emotions, because each facial expression might exhibit multiple emotions. You might be surprised and fearful at the same time. So now that for the data set we have probability distribution for the target, we have multiple ways to implement loss function. But before we go there, let's look at the network. If you look at here, this is a VGG network. However, VGG network was designed initially for ImageNet. ImageNet, the resolution is 228 by 228, and the number of images in ImageNet competition is huge. For this emotion, the data set are very small, and the size of the data set is 64 by 64. So if we use VGG as it is, we'll overfit on the data. So this is to show how easy you can modify a VGG network to be able, using CNTK, to be able to train on smaller data set. If you notice here, each of these blocks the same as you saw it before, so I will not go into detail, but usually we add a lot of dropout. We change the size of the dense layer. And of course, the output is 8 instead of 1,000. So let's go back about the loss function. Currently, we said we have a probability distribution for each of the emotion corresponding to each face. So now we can learn the distribution itself. So in the cross entropy, use the target distribution and use that as our target goal. Second option, use the majority. Pretty much select the emotion that have the highest probability and use one target and use conventional loss function as before. Third one, multi-label, which means we treat any emotion above certain threshold as the same. For example, any emotions that are more than 30% probability we'll consider as a valid answer. Probabilistic label is the same as the cross entropy one, but instead we'll learn the direct probability directly. We will select emotion in each iteration based on its probability weight. So pretty much we will sample emotion, and on the long run you should learn the distribution. If you look at those closely, only the multi-label are different loss functions than the other two. So here's the majority voting probability label drawing, probability and cross entropy. Here's their loss function is a standard cross entropy. As Sayan showed before, we have cross-entropy API loss function built in CNTK. You can use it, but here we want to show you how, if you want to implement your own one, or if you want to customize it, it's simple. You can use CNTK expression, and this one will create a small subgraph, and it will run on the GPU or distributed or whatever you want. Most of those low-level API are similar to NumPy API. You can do most tensor operation. Multi-level, the different that we get the maximum estimate of the sum. And those you can feed it to CNTK trainer and start train your network. So let's see some examples. This is output from from CNTK, and here's some of the images online and their corresponding emotion. And here a video. So that show you is a practical application for deep learning using CNTK, and how to customize pre-existing network to your application, and how to implement your own custom loss function. Next, we'll talk about faster RCNN. Faster RCNN, it's a detection algorithm that can detect most of the objects in the image, and won a couple of competition when it was first released, and it used a lot as a building block to a lot of image tasks that we want to detect, for example, all the car in the scene or object in the scene, and then process them after that. So we'll see in faster RCNN how to use pre-trained model, how to be able to concatenate and cut and slice network together, and how to clone the model, and I will discuss what we mean by cloning. This is the architecture of faster RCNN from the paper. So it's used at the bottom. It's any CNN. It can be VGG, it can be ResNet, or any pre-trained model. This one usually is fixed. You use it, it's trained on ImageNet. You can fine-tune it or keep it fixed. Then it have RPN, or Region Proposal Network, that propose that propose a rectangle or candidacy rectangle in all the objects that it sees. It can propose 300 rectangle or more or less. Then you have the ROI pooling, which ROI pooling is exactly like max pooling, but it run max pooling on each of those rectangle and keep the size fixed. Then after that you do two things: classification per box and regression. Regression will adjust the offset based on the ground truth to be able to have a bounding box on the object in the image. On the right here's the flow chart of the layer image. You have a CNN, RPN, ROI pooling, then the fully connected layer, and classification and box. These drawings that you see, this is a visualization of CNTK network of faster RCNN. Of course, you don't see the detail here, but the network is pretty big. And in order to make sure that it matches so the original faster RCNN was implemented in one version in MATLAB and one version in Caffe. We run Caffe version and our version and checked each node and made sure that the output match exactly. We fed it the same image. We made sure that all the random all the weight are determined, all the random generator are deterministic with the same seed, and we check exactly they are matching exactly and debug it layer by layer. Faster RCNN, it's a big network, so I will not be able to show it all here, but I will show the most important components that show you and how to express them in CNTK. So that's the code of creating faster RCN. Most of those are functions that create other helper functions that create other network. So we'll go on those on details. First of all, here's the CNN. We assume you have a pre-trained model in CNTK saved somewhere. You will load this model, and then you will clone this model. Cloning for us, cloning a model mean like create a copy or view of the model. We can clone model, it depend on the type here, clone method. We support freeze. Freeze mean copy the model, clone the model, but make sure that all the parameters are read-only. So when you clone freeze and use the cloned model in your network and train, nothing will touch those weight. So those weight will be fixed. We have clone method.share. Will mean we'll clone a model, but we'll share the weight with this model, but this weight can change. Also, we'll clone method.clone. We'll copy the weight, but you can change them after you copy them. So we have 3 types of cloning. Freeze mean the weight are frozen. You cannot update them during training. Shared the weight, and both networks that share the weight can update the weight. This is important for Siamese network and other type of networks that share the weight and both them updated. Also, you can do clone, which copies the weight. You will have 2 copies of the network. It's deep cloning, pretty much. And then each one can update its weight. And here, once the clone method, we set the input variable and instantiate the convolution. Then we'll create the RPN layer. The ROI layer next. ROI pooling is already built in CNTK pooling. The RPN layer is not built in, but it's implemented by 3 convolution layers. 1 base convolution and 2 branches, 1 for classification and 1 for regression. Then here's the thing that in RCNN, it clones the model, it clones the bottom of the model, the convolution part, and the fully connected layer part. Then it injects between them the ROI pooling. So this is clone from pool 5 to drop 7, and this do copy of the cloning, but we want to modify the network, and this one will feed it to the ROI layer. Those names that you see them, those are the name of the layer. When you create the network, there is a field called name equal. You can specify it, the name, so you can easily query them. If you don't specify the name, we'll generate one for you, and from the log, you can see the name and be able to use it. And here's the dense layer, as you saw before, nothing special about it. And the loss is the RPN loss plus the detector loss. Here, example of a toy example. So we have the faster RCNN trained on Pascal dataset and other dataset, but also we provide example, what if you want to run it on your own private dataset. So we'll select it a grossly dataset with only 17 classes, and you can train on them. And here you see the output of it. So this is a refrigerator, and this is the content of the refrigerator. So this is identify each of those content. Okay. So next, we'll talk about our artistic neural style from Leon paper and Roman paper. Artistic neural style, it's you have 2 images. You have a content image and a style image, and you wanna update the content image to have the same style or look like the style image, but without destroying its content. If you look at here, the content image here, it's an outdoor. Here is a style image. It's the star night image, and you want the output. If you look closely here, the output still have all the content of the original image, but the style and the coloring it's the same as the style image. So how they do that? Most of the trick on this one, actually this one is less neural network, the deep learning or the pre-train it's used to create the loss function, but there is no weight update at all. All the update we'll talk next is the actual image, and it can be done by any optimization library you have. So what they have a pre-trained network. You feed it an image, and from each layer, you regenerate the image, and you generate the original image. So the idea is that for each layer, you lose some information. If you look here, the generated image it still look like the original image, but there is a lot of distortion because you lost a lot of information. How they regenerate the image from each of the layer? They simply feed the original image and store all the future for each of the layer. Then input a white noise and get all the future of each of the layer. Then they compare them and keep changing the white noise until both match, and then you will get this image. So the output of each of the layer is the feature to see, indicate about the content. For the style, they do something similar, but instead looking at the output, the future output of each layer, they're looking at the covariance matrix or correlation of each of the layer by using something similar gram matrix. So the correlation here, according to the paper, it shows a style. And if you saw what it's drawing out in the top, it does not show any content of the style image. It shows them as the style or of the image itself, but there is no content preserved. So the main idea of artistic neural style or the main trick is that how to define a cost function. So here's the cost function of artistic neural style. The first two are from the first paper, and the second two is improvement on the second paper. So it's three terms. It's content loss, style loss, and variation loss. The content loss, it's simply for each layer, it matches the output of the layer of the original image and the image that you want to generate. And the implementation in CNTK, it's simply trivial. It's square error between X and C. C is the content, and X is the image that will keep changing to match C. Okay. Next, the style loss. As we say, the style loss is similar to the content loss, but the only difference, you compute the gram matrix of each feature of each layer. So the gram matrix is simply, it's the feature transpose itself. So you define it here, and then you use the gram matrix of X, of S, and then you compute almost the same error. The total variation loss, it measure of smoothness. So the idea is that the output image to look better, it needs to be smooth on it. So how they do it, they compute the delta between each pixel. So there is multiple ways to implement that. One of the easy ways is to simply run convolution, because the convolution and correlation are the same, and you define a kernel with -1 to 1. So when you apply this kernel on the image, it will actually compute the delta between pixels. After you define the loss function, the rest is not actually CNTK. Yeah. Yeah, please stop anytime if you have any question. Yeah. So after that, the rest actually is not deep learning or CNTK. It's just you have loss, you keep changing the input image or the white noise, and then compute the loss and do it again. The example we have, this example we use SciPy to do optimization on this loss. But the artistic style, the deep learning only involved in computing the loss function and nothing else. But the weight remain fixed. No, both images. So you have the same network. You feed one image and store the output of each layer. Then you feed the style image and you store the output of each layer. And those output, you don't need the network for those images anymore because the weight does not change. Then you feed the same network a white noise and a blank image that have white noise. Then you compute the feature of each layer. Then with those features, you compute the loss function by comparing the square root of the feature of the white noise with the feature of the content image and the correlation of the white noise with the correlation of the feature of the style image. Then you keep modifying the image that you want to generate until, and then recompute the loss again. But to compute the loss again, you just need to feed this image, the X value, to the network, because the content and the style are static, won't change. And you keep doing that until the loss goes below certain threshold. Okay. So next we'll talk about, again, generative adversary network. GAN, it was published in 2014 by a good fellow, and we have two tutorials on GAN, basic GAN and DC GAN. So in GAN, we'll see the takeaway for the GAN, we'll see how to train subset of the parameter of the network and how to implement a non-standard learning algorithm. Of course, again, now it's well known now, but when it got released, it was totally new way of, or different way, a new way to train. So GAN is inspired by Minimax algorithm from gaming theory. It have two networks, a discriminator network and generator network. The generator network generate data, and the discriminator network judge those data are real or fake. And those networks try to compete against each other or outdo each other. Once reach steady state, the discriminator should be powerful enough to distinguish between fake and real data, and the generator should be good enough to generate fake data that look close to real data. Usually the training of the GAN, it starts with the two loop interleave between discriminator and generator, and there is a lot of tricks, and there is a great site that have all the tips how to converge GAN, because it's difficult to converge. So here from the drawing, you have a real image, and you generate a random vector Z as input to the generator. The generator usually have a bunch of convolution transpose or upsampling that generate an image the same size as the real image. And both get fed to the discriminator. And the discriminator, when it fed, it needs to decide if the input is from the real image or from the fake image. And we keep iterate the discriminator loss function, try to penalize the fake image, and the generator loss function try to make the discriminator believe that it regenerates a real image. Yeah. So here, again, a full GAN implementation, assuming you already have the generator and discriminator itself are a standard network. It can be a convolution or feedforward network, nothing special about it. So we assume you have a function called generator that creates a model similar to any of the model that we discussed before. So G is the generator network. It takes a vector and produce an image. Then the discriminator take an image and produce a probability for a single item. So if it's 1, mean it believes that the input is real. If 0, mean it believes the input is fake. So the discriminator, we will feed it both the real and the fake image. So we need to clone it. And in cloning, we have also features that you can substitute variable inside the clone network with your own variable. So here, this is the input variable we use to only feed it real image. So we want to have the same discriminator with the same weight. So we clone it, we share, and we substitute the real input with the output of the generator. So now D real and D fake share exactly the same weight, but one take real image and the other take fake images, or generated image form, takes the output of the generator. Now this is a loss from the paper, nothing special about it. The generator loss try to make the discriminator believe that its input, that fake discriminator output 1, and the discriminator loss try to penalize the fake discriminator and improve the real discriminator. In both cases, when you define generator loss, you want to make sure to only the generator weight get updated. And discriminator loss, you want to only the discriminator weight get updated. To do that, here, CNTK Adam learner optimizer, it have a parameter you can specify the list of parameters that it need to update, that it only can update. So here, you specify g.parameter to it. For the dlearner, you specify d.parameter. So only the dlearner will update the discriminator parameter, and only the glearner will update the generator parameter. And then you will have two trainers, one for the generator and one for the discriminator. Any question? So you have two networks. You have two loss for each of the network. Each network try to outdo each other or compete against each other. So this is why it's called adversary. The adversary between two networks, similar to min-max algorithm. But so the generator network try to let the discriminator return 1 when it gets its output. And the discriminator network try to only return 1 when it gets real image. And during training, each one try to improve its own only weight to do better job in be able to discriminate or generate. Okay?
It's really nice to have like the share or the substitution explicit in the definition. But is this like flexible? You can just like freeze some layers.
Yeah. Yeah, the RCNN before, some of the code I didn't show because just the place and the time, we have it in our example, we cut pieces of the network and concatenate them, and you can freeze pieces and not freeze other pieces, so you have you have a lot of flexibility.
Isn't that where you showed that the pool to get
Yeah, yeah.
that you
Yeah,
clone that piece?
exactly.
And you can name your own layers, so it's highly recommended that you do that, so that you can selectively clone and even investigate any partial results that you may want to present.
Yeah. And this is the output from the CNTK code from Amnes data. This is generated output by the generator. So Amnes data, it's OCR data or a number data that you usually use for people trying different algorithms on OCR. It's simple data, but it's very good to start with it to try different algorithms. Next, we'll talk about Pixel CNN. Pixel CNN was originally published by Google Mind, and the latest publication was from OpenAI by Tim Salman, which they called Pixel CNN++, which they add a lot of improvement. Pixel CNN, it's the original implementation is available on OpenAI side. It's done in TensorFlow. We ported in CNTK and also matched the number. One of the interesting things about Pixel CNN, its implementation, it depends heavily on tensor operation. So this one will show you how to use CNTK simply as a NumPy on steroid. And the advantage of Pixel CNN compared to GAN, Pixel CNN is generative model. It generates images, but it generates the probability of each pixel. So you can sample images that it generates. One disadvantage of it, it's slow because you need to generate pixel by pixel. So in Pixel CNN++, it model each pixel as a mixture of logistic probability. It learns the condition probability of next pixel given the previous pixel. To generate full image from Pixel CNN, you need to feed it a white image or a blank image and generate the first pixel, then feed the image again, generate the next pixel and feed the image again. So you feed the image n time, and n is the number of pixels in the image. Also, it can't train conditionally by the label, so you can specify to generate, for example, all images for aeroplane or all image for a specific label. This is the network of Pixel CNN. If you look at the number in above, the image is 32 by 32 because this is CIFAR image. You go down until 8 by 8, and then you go up again. Going down sample and up sample helps the network to learn long dependency. And it have shortcut connection between next layer and between skip layer. The network itself is pretty big, so we'll not show it here, but it's available in our example. But here one section about something called gated ResNet that they implemented. So here we have a convolution. This is name is network in network. It's simply one-by-one convolution, nothing special about it. Then you have a dropout, and then you pack some of the data in a tensor, and you need to unpack it back. So here, if you guys familiar with NumPy, most of the power of NumPy dealing with the indices of tensor are available in CNTK. So you can do, you can slice range of the tensor, you can slice one from the end, and most of this operation we are trying as much as possible to match NumPy behavior because we know most people that use Python are very familiar with NumPy. Yeah, there are some naming difference, but the mapping are very easy. Yeah. So instead of importing NumPy, yes, import CNTK as C, and then use C dot on all of the stuff instead of NP dot. Yeah. But most of NumPy operation, we have it, and we have, of course, extra operations that are pertaining to deep learning, but most NumPy operation and most NumPy, and we also made sure that our API interoperate with NumPy, so you can easily convert to NumPy and convert it back, and you can, so we try to make sure that you feel that it's part of the API, it's a first-class citizen Python API. Here's some of the generated output of pixel CNN. Those are cipher data. Okay. Any question? We have it in the example. I don't have it here because of the size, but yeah, the loop, it's simply you start with creating an empty image. You feed it to the network. Then you copy only the first pixel, and you make sure that in the output you mask all. So when you feed it in the network, you only copy the first pixel, and you feed it again. Then you copy the 2 pixels. So you need to make sure that the next pixel, only the previous pixel are available, and you do that n time. It's not complicated. It's just slow. Okay.
It's in our GitHub site.
Okay, guys, thank you for coming back. So let's start. Okay. So let's continue some of the other some image tasks and how to implement in CNTK, and then we'll move to video. Please feel free to ask any question anytime. So the next topic is image caption. While it's great to be able to classify an image for a specific object or what is the content of the image, be able to describe it in English or in human word, that actually more impressive, and be able to understand the content and the relationship between the content of the image. So in the image caption, we'll see how to handle variable length sequence, because each image will have a sequence of words. It can vary in length. And we'll show how to implement a block function in our API. So if you look at here, you have the input image. Usually you don't deal directly with it at the pixel level. You want a high-level feature, so you pass it through a pre-trained model, similar to the models that we discussed in prior, can be VGG, ResNet, Inception. Then you use this pre-trained model and use the label to be able to train a recurrent network to be able to retain a recurrent network to generate a sequence of words based on the input image. However, we have one problem, is that the image in different space than text. You cannot compare them together. So how we usually handle that is to map both of them to a space called embed space. And this learned during training. A word, it's usually mapped, you convert them to one hot vector as sparse, and then you map them to a condensed vector, use embed, which is the E here. Now you have the future and the embed. This embed is learnable. You can concatenate them and use this as a future. So each input will be the representation of the image and the representation of each word. This only for single word, and will keep sending as a sequence. Embed, it's simply multiplying a matrix or a weight to the input to map it to a different space, and this weight is learnable. We have built-in embed functionality in CNTK that you can use directly. You specify the embed dimension. It's usually much more less than the input dimension. And here is the input feature. Okay. Currently, the image is a single item, and the words are a sequence. So we want the single item or the feature of the image be repeated for each sequence. To do that, we use broadcast as. What does broadcast as do? it maps this image to a sequence. And it will be repeated the same image feature. So image feature, that usually is the last layer of a feedforward network, which usually 1K or 4K. So this is mapping the input pixel or the image to high-level feature, pretty much a vector. That should in this vector represent the content, the visual content of the image. Then the embed map the English word, like person flying, to another vector, and this part is learnable. So during training, those should be mapped to the same space. Once they are in the same space, you can learn the relationship between them and be able to generate a sentence from the image itself. If you look at here, a person flying a kite, you notice there is a symbol here, S, and there is symbol in the output, WAC S. To train a caption, we usually need to know the start and the end of the sentence. To do that, we define a start token and an end token. And that, during training, we know that the sentence, because it's variable length, we need a way to know the length or know when to stop. So, and because recurrent, it's unrolling and can unroll indefinitely, we need a way to stop, to know when to stop. So usually, each sentence, we envelope or wrap with the two special token, one called the start token and one called the end token. The start token is the one we know we start now decoding, and the end token we know stop decoding. So we'll see how, assuming we already train a network, how to evaluate the network. Okay. So this is, we'll use a greedy algorithm to evaluate a network. Training sequence to sequence, it's, we have a lot of examples here, but they don't fit in the slide, but we have a tutorial in our site, and here's the link to our sequence to sequence tutorial, which have more than one algorithm for sequence to sequence. So here we use the unfold from. It's a CNTK API that take a lambda, and it takes the input and generates the next output. The next output, we pass it to a hard max. Hard max, it's like soft max, but it generates 0, 0, and only 1, 1. So it generates pretty much one hot vector. This output, the unfold function will feed it first input, get the output, use this output as the next input. So it will be added to the history, and keep doing that unrolling. So once we learn it, the first input will be the start of the syntax, and the image appended with the image feature, like this one, it will generate A. Then A will be fed here. It will generate person. Person will be fed here. It will generate on. On will be fed here, and so forth, until you get the end token, which is this one, and it will stop. Of course, you can implement it manually in CNTK, but we already have, because sequence to sequence and one to many and many to one, all those are well-known network. We have a lot of APIs that cover most of them, so you can write it in condensed matter, and they have been properly tested. So again, this is how to evaluate or generate caption from image after you train. The input, it will be the feature of the image, concatenate with the actual representation of that start token. This is the first input. The first input will be fed to the unfold from. Unfold from will generate a person, the first word, which is A. Then A will be appended with the input and fed in, will generate a person, and this will be appended and generate the next word, and so on, and will stop only when we see the last syntax. In training, we don't feed it usually the output of the recurrent. We feed it the ground truth, and we update the weight to match, and we usually have a soft max on the top. Okay. Next item, image segmentation. This is a project inside Microsoft. They need to do image segmentation on limited resource device, and they focus on portrait. So this is their output. You have an image, and it generates a mask in which the foreground is white and the background is black. The network looks a little scary, but if you look at it in details, it's actually all the building blocks that we discussed before. There is nothing unique or special about this network. Those usually, there is a lot of trick that was in a lot of papers that used in this network, but all this network is first you downsample, then you upsample, and you have some skip connection. This network is one of the special part, it have feedback loop, which usually it's used in recurrent, but this one not for recurrent. So the output mask is always also fed as an input. This one used in portrait from a video sensor. So this is why they fed the output to be able to use the previous output to improve on it. Okay. We will show thus just the skip connection part of this network, and as you see, it just get repeated. So here how you implement a skip connection, which is similar to what we implemented in ResNet, but it's the stride or the distance is a little longer. Here you define your network, Z. This is a small block in the previous network, in this network. Then you define convolution, it's batch normalized, and the activation. You repeat this 2 times. Then with the for loop. And as you notice, we here have the I index. Before we use the I index for the future of the convolution. Here we use it for the size of the kernel. So we select the first convolution is 1 by 1. The second is 3 by 3. So you can have a list of tuple, and the I will select which one depend on when the for loop expand. Also, all of them will be initialized with gloret uniform. Then we have 1 by 1 convolution at the end, and then it's batch normalized. This is the part of the block before the skip. Now we want to add a skip connection. So simply we want the input to be connected to the output. So the output here is Z plus input, and we return it, pass it to a ReLU nonlinearity. So if you look at here, this is the block, and this is the block, and this is the skip. This technique usually used a lot, and especially recently, to be able to see downstream layer, see future from, downstream layer, see future from upstream layer. Usually, as the layer closer to the image have much more granular feature. The layer far away from the image have much more abstract feature. So sometimes it depends on the task or the problem we are trying to solve. Having the high layer also see the more granular feature, it gives it some power to certain tasks, especially if you want to preserve some special information. And this one we do segmentation, so special information is important.
If you had a case where you're feeding back, how would you describe that?
We actually,
Z is going back to the input.
yeah, this one is feeding back, but is not recurrent. So what he does, what they do here, they generate an output. The first mask is black, there is no foreground. Then generate the output, and then the next input get concatenation, and that force. There is no unrolling and no special treatment similar to recurrent network. So yes, it's recurrent, but it's only the previous output, and there is no unrolling or like RNN.
So is there, like, as you feed this, the finer grained features towards the downstream, does it help correct the edges?
This is the input to this video. So this one, it's C2 frame. So it helped to correct because usually in video, it's 30, assuming it's 30 FPS, usually the change between 2 frames are very little. So usually the mask on the previous frame is almost the same as the mask of the next frame, might be more shift. So this helps the network to only adjust it for the next one, yeah. And as you see, because this segmentation, the output need to be the same resolution as the input. because you are per pixel decide if it's classification. Each pixel you say it's foreground or background. Okay. And this one of the example, and we see the background. The background is get replaced with different background. Okay. And this is what we have for the image part. So before I move to the next section, does anyone have question? So now we talked about image, and we go to various image algorithms and how to implement them to CNTK. Now next we'll move to a video and see how we'll be able to do. We'll focus on action recognition and how to be able, we'll implement multiple algorithms to recognize action from video. Okay. Usually in action recognition, there are two problems: action classification and action detection. Action classification, you have a video that is already trimmed, have only one action, and you are output or classified the video as which action you are seeing inside the video. Action detection, you actually have untrimmed video. It can have multiple action or no action at all. You usually need to find where the action start and end and what the action. So you need to find the location and the corresponding classification. Most action detection algorithms are usually based on action classification. They use whatever is moving window or some variety of action classification algorithms. They use those on action detection. This is why we will focus on action classification. Okay. Action classification, there are tons of algorithms how to do it. There are some algorithms, and they actually provide good result that don't use recurrent at all, use feedforward network. Some of the algorithms extend convolution to 3D convolution, and the third dimension is a time domain. So that, and usually 3D convolution have been proved to learn the local motion or short-term motion between frame, and use normal feedforward network, or using 3D convolution or be able to use feedforward for a video. There are multiple ways to do it, and we'll discuss that next. Another approach is using RNN, and to be able to have variable lengths and understand the dynamic of the video. In this type, they usually use a pre-trained model, similar to what we discussed before, VGG or ResNet or frame to the pre-trained model, and then extract the feature from one of the layers, usually is the last layer, which around 4K or 1K size vector. So now you replace the video sequence with the feature sequence, and each feature is 1K. Then you feed this feature to standard to RNN network or LSTM or GRU network, and you classify it or learn it. We will look at both implementation and how we can implement them in CNTK. Okay, this was from Karpasi paper. When they released the sport, when he was intern at Google and released the sport 1 million data set, they show different algorithm, different feedforward algorithm to do action recognition. First, you can forget about convolution 3D, use standard convolution and standard image single frame. You can do that by selecting multiple random frame, and then you can average the output or do something like that. Or you select only one frame. This, of course, usually does not produce any good result. Early fusion, which we'll see the implementation next. This one, similar to this one, is a feedforward network that uses 3D convolution, so it's fuse the frame at the beginning. Late fusion, also we'll see this one. You can use 3D convolution or also 2D convolution and have two branches of the network all the way till the end, then fuse them at the end. And then there is the slow fusion, which means you do it step by step. Pretty much they try all possible combination and see which one works. So, okay. So let's see how to implement 3D convolution in CNTK. Our convolution is actually very generic, can run on any dimension. We have aliases to make it easy, visible in the documentation, convolution 3D, but the base convolution support any dimension, you can throw it at it We don't have a limitation for that. So this is a network inspired from VGG that use 3D convolution. As you see here, the only change is that we use convolution 3D instead of convolution, and we have the kernel 3-dimension. And the input variable, now it have an extra dimension, which is the sequence length. So this is number of channel, sequence length, image height, image width. Okay? So pretty much, to convert a network to 3D convolution, it's almost the same as a standard network. The only difference, you just extend your kernel and use convolution 3D. Nothing else you need to do. And this one is the fully 3D convolution that work, and we have it running on video data in our example, and also converge. Yeah. Okay. The second part is late fusion. Late fusion, it's actually as simple as early fusion. You define two networks, which is first network here. You don't have here a fully connected layer. You have convolution 3D, max pooling, convolution and max pooling. You have, this is, we store it in Z1. We have another one, we have the same network, Z2. Keep in mind, this one use input variable 1, this one use input variable 2. So, because one for that and one for this one. So here, we define two input variable, 1 and 2, one for one branch and the other for two branch. All of them, both of them have exactly the same dimension. Which now four dimension, because you have the channel, image height, width, and the sequence length. And then after that, you define your dense layer, which is a 2 block at the top. And then the input to the dense layer is the concatenation of this one and this one, Z1 and Z2. So in few lines of code, you can do late fusion. To do the other one, that multiple fusion, it's much more easy. Just keep defining each branch, concatenate each branch, and of course, you can wrap them into helper function and keep concatenation into it, okay? Any question? Okay. So let's go to the next step, which is the next algorithm, which is using RNN. So in this one, we load a pre-trained model the same way as we did it in faster RCNN. We will extract feature from each frame in the video. After that, we don't need the pre-trained model. We don't need the video. We only can save our feature into separate file, and then we'll use this feature as the representation of the entire video. And then we feed that to our RNN network. We will use both LSTM in one example and GRU in another example. And then with the LSTM network, we will use it to classify the video. How many of you know LSTM and RNN and the difference between both? Okay. So just a quick background. RNN it's a very simple network. It's one node that feed to itself. This is the classical recurrent network and the first one that define. The problem on RNN, you remember when we talked about ResNet and we saw about there is a skip connection that helps the gradient to propagate to the back. In RNN, they have the same problem because you unroll the RNN in time domain. So the actual network is big, depend on the sequence length. So the problem in RNN, two problems. The gradient vanish, which called the vanishing gradient problem, and or sometimes it explodes, which go to infinity and you get NaN in your training. So the vanilla RNN usually are not good for people to use it to train long-term sequence. It will not learn anything because the gradient will vanish to 0, or you will get NaN in your training because it will explode. LSTM was released to solve this problem, and there is a very good blog about explaining the detail of the LSTM. So they add multiple node or node inside it to learn when to reset the state. And they add also, similar to ResNet, a shortcut to be able to flow the gradient without any reduction. And this the LSTM is the reason that RNN now can learn long-term sequence and used in a lot of practical problem. So the LSTM is a variation of the RNN. It's a little more complicated that actually handles the vanishing gradient by use some skip connection and some gates that can reset the network. GRU was published recently in 2016 or 15, I believe, and it's similar to the LSTM, but it's much more, have less node internally and provides almost the same result. In CNTK, you don't need to know the detail of them. We have LSTM block, GRU block, but if you need to create your custom RNN cell or unit, then you will need to know the detail. Okay, so we have in our CNTK website all the pre-trained models that we trained. Feel free to download them and use them to your own problem. We have for ResNet multiple size of ResNet, like ResNet 18, 50, and others. We have for Inception, and we have for VGG. Also, if you have a pre-trained model you want that we don't have it, if you have it in another toolkit such as Café, you can download it and convert it, and Shah will talk next about it. Or if you want to train your own network on ImageNet or other image data set and use that as a pre-trained model, you can. So you have 3 ways to use a pre-trained model. Download from our website, use pre-trained model from other toolkit after conversion, or train your own pre-trained model. After you train pre-trained model, here how to load C is alias to CNTK. So usually at the beginning of your Python, you say import CNTK as C. Load model, this is the path to your model file. Then we have a function called find by name. Load model in itself is not enough because you want to extract feature to a certain layer. Usually each layer or node have a name. If you don't specify name, we will generate one. So you can find the node by its name and it will return the root of the graph. To convert it to a graph that you can execute, you use the S composite. So how now to extract feature? Just output node.eval and feed it the entire image, you will get the feature, and that's it. So you will loop through each frame in the video. You will call each frame on each frame output node.eval. You will generate a feature, one-dimension feature vector, and you can save it in a file to use it for LSTM. Any questions so far? Okay. Okay. As Shah talked at the beginning, one of the strengths of CNTK is variable length sequence. So I will not repeat that again, but just as a reminder, here how we deal with variable length sequence, we rearrange them within the mini batch to reduce the number of empty space and be able to make sure we don't stall any GPU while processing each row in parallel. So each row here gets processed in parallel. So the idea is that if we can make them the same length, that will be the fastest way. So we pack them in a way that reduces the empty space here, so each row is the longest possible. And we keep track with all those barriers, so we can reset the LSTM when we reach them. From the user point of view, you don't need to know you don't need to handle anything for variable length sequence. You just pass it, and we will handle that on your behalf. Okay. How to implement what we shown before for the sequence? We show past value and all those great, but those are the low-level API. We have high-level APIs that handle most LSTM algorithm or network, like LSTM with peephole with other variation, GRU and others. And to be able to use LSTM, instead of using CNTK.input, you use CNTK.sequence.input. That's the only thing you need for the input to be variable length sequence. You define your network as if you have a single sample. We hide the dimension of the sequence and the batch. You can access them if you need, but most cases you don't need. If you need the last output of the sequence, you use .last. We will see all that in code next. If you want the first input, you do .first. Okay. For variable, for a sequence to be able to classify action using LSTM, usually you have, this is a feature that we extracted per frame. We feed it to LSTM. This is each row, how the LSTM unroll in time. So this is time axis. Each column is actually the number of layers. So we'll use 3-layer LSTM, and we will feed it a variable length sequence, which is the future represents the video. For the last layer, each cell or each unit of LSTM produce an output. However, in classification, most of the time you don't want the output in the beginning because they didn't see enough data to understand what's happening in the video. In this example, we use the last output based on the assumption that the last output, the LSTM cell saw all the previous frames, so it have enough knowledge or context to know the action. There are better algorithms than that learn where to look, but let's go for the simple one for the time being, okay? So how to implement that in CNTK? As we said before, use sequence.input variable with the input dimension. Input dimension is only the feature size. Does not have the sequence length because it's variable. You don't need to specify. You can specify, of course, you need the label. Then you specify sequential, so we'll stack multiple layers together. The first layer, we want a 3 LSTM. So range 3, recurrence, recurrence is our engine that call the past value and future value to be able to iterate on it. So you call recurrence and then specify the type of cell. We want LSTM. And you specify the size. Hidden dimension of the LSTM, it's hyperparameter. You need to specify based on the problem. You might need to try multiple ones to see which one fits your problem. And that's actually it. That defines this part entirely. 3-layer, range 3, recurrence, LSTM, hidden layer, and variable length. We said we want get the last one only to classify if the type of action. We use c.sequence.last. We read the last input in the sequence from the last layer. Then we put a dense layer to classify it as a softmax. Any question? And that's it. This is the entire graph implemented in 3 lines of CNTK. Let's go by direction. If the video is not streaming, then there is nothing prevent me from looking this direction and average or sum the result together. Sometimes in a lot of data, this provides better result because usually if the sequence is long and you only read the last one, the network itself might not be powerful, efficient to still remember the first few frames. So having bidirection sometimes improve the result. So how to implement the bidirection in CNTK? It's almost the same exactly. The forward pass here, this is from from left to right, the same as we did before exactly. If you notice here, I switched the cell type to GRU. GRU is very similar to LSTM. It's faster, but it's very similar in terms. It's also avoid vanishing gradient, and it's also well used. We have it as a built-in API in CNTK. And you specify the last as we talked before, and you pass the input variable. To do the backward pass, you do exactly the same, except you specify go backward through. However, when you specify go backward through, you don't need to get the last item because the last item in backward is the first item. You want to get the first item of backward, which is the last item in backward. So if you look here, sequence.first. And then just concatenate them. Some people do average, so there are multiple ways to deal, and then pass to a dense layer, and this one will pass to softmax. And this is bidirectional classification for video data. Any question?
So the softmax is a default? Is there a way to
To specify what, sorry?
The softmax was the default. How did you tell us softmax?
No, usually if you have multiple classes, we use softmax. But in CNTK, most of the time, you output dense layer, which is the one before softmax, because our cross entropy, it have built-in softmax in it, because that's much more faster to run than have it separated. But usually, softmax, it's used if you want to classify multiple classes. If it's binary class, then you use binary classification. If it's regression, you can use different lots, as we discussed before. But usually, in most classification, people use softmax. Yeah. There is no softmax in this slide. Yeah.
Next step, that's
Yeah. Yeah. This one defined in the previous slide in the network when we specify the cross entropy with softmax. Yeah.
So this model, the C is out as the model, it will lead to a loss function along with your ground truth. And at that point, you can specify what your loss function should be. And
Yeah.
usually for classification, we choose cross entropy.
Yeah.
Yeah. I mean, this is up to the input.
Yeah.
Input and the softmax.
Yeah, the reason we did not specify it here because we mentioned before, but here is a focus here on how to implement sequence and bidirection. Yeah, okay. So you need to go backward through and get the first one instead of the last one, and that's it. Okay.
If you're dealing with sequences where you have patterned things up, you can imagine how much logic you would have to put in to make it.
Yeah. Yeah, implemented those code in different toolkit. You will implement way more code to handle a lot of corner cases. Okay. Okay. Any more question? Okay. Okay, this is what I have in video, and then next will be Sean.
All right, so Emad had showed you how to write CNTK models, and I hope you have been convinced that it's quite trivial to write either convolution or recurrent, all kind of networks. So I'm going to talk to you a little bit about parallel training, and that is actually one of the strengths for CNTK. I'll talk about how can you enable parallel training and a few parallel training algorithms that's built in CNTK that actually is very effective. So just to remind you that if you want to do distributed training, you basically follow 3 steps: prepare data, configure your reader, network, learner. These are all standard with or without doing distributed training. And then during training, you basically says MPI XC, and then number of nodes, and then host what are the servers, and then just run that. So it's very, very straightforward. Now, I think in the first introduction part, I also mentioned this slide where you want to do data parallel training. Then there is this ring algorithm that's very efficient. But for dense networks, they might not be good enough. So I mentioned briefly 3 different algorithms: 1-bit SGD, automatic mini-batch sizing, and block momentum. So in this section, I'm going to give you a little bit more detail about these 3 algorithms, as well how you can use them in CNTK. How do you write code? So this figure basically shows a cost analysis of different procedure, different duration when you do, say, gradient aggregation for distributed learning. So essentially, there are 2 major costs in deep learning for in the distributed manner. So there is a variable cost, and that is essentially to calculate the gradient with data parallelization. This is scalable to the number of nodes that you use. The second cost is a fixed cost. So these are the costs where once you calculate the gradient for each node, you want to process them. For example, you want to do a momentum or aggregate accumulation, and these are fixed costs. And then you add the gradient to the model, which is also fixed cost. So, and then this is the calculation part. And then you have the communication cost, which is the cost you need to pass these gradients to each other. And if you can see that, well, if I can reduce my communication cost, then I can definitely make the overall thing faster when I scale up to more than 1 GPUs. So the idea of a 1-bit SGD is to reduce the number of bits being exchanged between the servers. So here's the basic idea. Instead of exchanging full precision gradients at 32-bit, in 1-bit SGD, you quantize these gradient into 1 bit. Now, you certainly would worry, well, my training accuracy, my model accuracy probably suffer because I'm only looking at 1 bit. So here's a trick that was done in 1-bit SGD. So essentially, after transmitting the 1 bit per gradient, you basically record how much residue you haven't transmitted, and you carry it over this error to the next mini batch. Next time you communicate, you add your residue to the gradient first, quantize again, send 1 bit, record the residue, so this just keep going on this way. And this way, we have done experiment and show that basically you don't lose much or any precision in the final model accuracy, yet you are able to reduce the communication cost by a factor of 32. It's extremely simple to enable 1-bit SGD. You practically don't need to write, just one, here is just 1 line of code. So in CNTK, you have this data parallel distributed learner. So this local learner is a learner which you typically write when you do not do distributed learning. So if you want to enable distributed learning, you basically add 1 more line to wrap the local learner into a distributed one. And then you specify number of quantization bits. So you can say it's 1 bit, or you can do 8 bit, you can do any bit you like. And then you apply the trainer to the distributed learner, and that's it. So CNTK does everything in behind for you. You don't need to worry about any, how do I aggregate gradient, how do I make sure everything runs in parallel. So these things you don't need to worry. CNTK takes care of everything for you. The second idea of improving the communication is to do automatic mini-batch sizing. So there's basically an observation that is given a particular learning rate, there is a maximum mini-batch size that will ensure the model will converge. So in CNTK, we use the sum gradient instead of average gradient for this. So this work is actually published in ICASP 2014. So the idea is that you keep shrinking your learning rate every once in a while, and then at any learning rate change point, you try a range of mini-batch sizes on a small data block, and then you pick the largest feasible one and then train. So what has been found is that when your learning rate drops lower and lower at the end of the training cycles, so at the beginning you usually like to use a larger learning rate as well as a smaller mini-batch size. But when the learning rate drops lower and lower, the automatic mini-batch size searching algorithm will typically find that you can use a much bigger mini-batch size over time. And there was this paper essentially shown that with such an automatic mini-batch sizing algorithm, at the later stage of the training, things can go a lot faster. And then you do not really sacrifice accuracy. In CNTK's tutorials, if you go there, there's a tutorial 200 that actually shows you how to do this automatic mini-batch sizing. And on MNIST data, it shows that if you scale the mini-batch size over time, your accuracy doesn't drop, but your speed improves very significantly. And then recently, there is a paper from Facebook talking about training ImageNet in 1 hour. This is particularly talking about ResNet. So the idea there is basically after a warm-up, you can start using large mini-batch sizes. And of course, the learning rate needs to be scaled linearly. And they show that it doesn't really hurt accuracy. Now, just to compare against what we have in CNTK, so in Café 2, they were using average gradient, while in CNTK, we were using sum gradient. Actually, today, CNTK allow you to use both sum gradient or average gradient. It's up to the user to decide what to use. But the default behavior of CNTK was to use some gradient. And then in that case, all you need is just a fixed learning rate. You don't need to change any single thing, and this behavior is natural. And so if you don't change your the learning rate, then you can consider this as a special case of the previous many batch sizing approach, except that you don't really change the learning rate, but you do research again and again, and search the best mini batch size again and again to improve. We also did some experiments to verify Facebook's findings. So this is still ongoing study. It hasn't been really finished yet, but here are some preliminary results where we show that on 8 GPUs, so Facebook can achieve about 23.6 accuracy, top 1. Error, top 1, and we are at 23.34. We're slightly better than Facebook's results. And on 128 and 256, we're seeing very similar numbers as what Facebook found out. So we do observe some slight degradation when scaling to more GPUs. So that's why we are continuing investigating what's happening. We also did experiments on BN Inception, so that's the first GoogleNet. And that one is a little more tricky because the learning rate decaying is not predefined, manually defined. It uses the exponentially decaying learning rate. And we also found that gradual warming up trick is useful in BN Inception, but you cannot achieve the baseline accuracy when the number of GPU goes to 256. So we're continuing investigating and see what we can do with this approach. The third approach is called a block momentum. So this is a pretty new. Last year, I believe, in ICASP, we published this paper by a few researchers in MSR Asia. So the idea is you basically partition the training data set into multiple blocks. And then each block can be further divided into multiple splits where the number of splits matches with the number of nodes you want to operate on. And then the training data set is processed block by block. That's called incremental block training. So here's the kind of the typical process of doing parallel optimization or training. So you first select randomly a unprocessed data block as DT, and then you distribute the splits into unparalleled workers. And start with a common initial model denoted as W init. Each worker starts to optimize its own local model independently by sweeping through the data splits. And then the most naive way is after all of them finish, you say, let's average the unoptimized models to get the new WT average. Now, the reason that this approach is effective in reducing communication costs is because you can control how big the split size is. So you can say, I want to train 100 mini batches before I do this model averaging, or I can do 1,000 mini batches before I do it. So you reduce the frequency of communication to improve the overall speed. One problem with this, though, that with model averaging, like here, where you strictly take the average of all the models, you tend to get a slightly worse accuracy for the final model. So our researchers find a new algorithm that's called a blockwise model update filtering. So essentially, instead of directly computing the W average, the new weight average, and directly replace the previous weights, here we calculate a model update, which takes the average and subtract the initial weight. So you create this delta or GT here in the first equation here. And then we use a similar idea that is the momentum equation to use a small delta to represent how much we're going to update the overall model. And with that, since these GTs are computed per block, this is called block momentum. And with that, you can update the global model by just adding a small, the delta t rather than the original gt. And that shows to be extremely effective in smoothing out the block momentums and make the whole model converges much more correctly. So in practice, basically you repeat this until all data blocks are processed, and then you repartition the data, and then you repeat until you obtain the final model. So in experiments, we have seen that this block momentum actually achieves better results, even more accurate than 1-bit SGD, and it also scales better than 1-bit SGD. And in order to do this, again, it's just one line of code. So you take the local learner, you wrap it with this function called block momentum distributed learner, and that's it. Then you just run the MPI exec, and then you're done. Any questions so far? Okay, so let's move on. The next topic is how to port models from other frameworks, in particular Caffe. And so in CNTK, just end of July release, we'll have a 2.1 release by end of July, and we will be include a component called Crosstalk Caffe. This is an easy-to-use tool for converting Caffe models to CNTK. So you take both training scripts, or you can take a model. You don't need to know anything about CNTK or Caffe. It's quite easy to use. The framework that we take is essentially you take, say, a Caffe model, you convert it into an intermediate representation, and then you take the intermediate representation and convert it back to a model, which in this case would be a CNTK model. And of course, you can do the other way. We haven't really enabled that in the Crosstalk Caffe, but it's very easy to go from a CNTK model to a Caffe model as well. And with this Crosstalk Caffe, we also implement a debugger that can be used to validate the converted model. So basically, we feed random data into the converted model, and we compare the output. And we have shown that many of the models we converted can reach up to 10 to the minus 6 or even 10 to the minus 8 accuracy, numeric accuracy. So that makes sure that we are getting identical models in the end. And this will be released very soon. So here's how you're going to use it. First step is you're going to prepare the Caffe proto text and a model. And then you configure a config file. So I will show you later how the file look like. You basically specify a source server, a model server, and a validation server. And then you do the conversion with one single command. So here's the configuration file, how the configuration file look like. I don't know if you can read the text. So the source server basically specify the source is Caffe. Here's a model path. Here's the weight path. And then the second model server specify this is a CNTK model path. And then the server essentially, this is the last one is basically the validation part. It specifies what kind of random data. In this case, is a random number from 0 to 255. And then you just do it. Just call the command and run it. And here's another example of ResNet 50. I mean, it's extremely simple to use, very, very straightforward. And we have a number of Caffe converted models shared on the CNTK GitHub website as well. They do reach extremely high, accurate compared with, it's like almost exact matching with what Caffe produces. So the current status is that the executable tool and source code will be there. We have been testing this tool with all mainstream CNN models. We have tested with AlexNet, Network Network, VGG, GoogleNet, ResNet, etc. We also use it to convert fast and faster RCNN as well as RFCN for segmentation. It does support CNTK user-defined functions, and the the validation model is provided to monitor arbitrary nodes between Caffe and CNTK. So it also helps ease the task of converting training scripts between Caffe and CNTK. And this is widely used for internal model conversion debugging. And that's all for the model converter part. Any questions? The reverse conversion is going to, I mean, if there's a request for such a reverse conversion, we can do it very fast. Because, yeah, it's just the same intermediate representation, just the other way.
How are your models stored?
Excuse me?
How are your models stored in time?
The model is stored in proto text kind of format.
Is the source pre-readable that it generates, or your own generated model?
Excuse me?
It generates source also, right? Converts the source.
It converts the Caffe script for training and convert to CNTK brain script. We don't do Python because it's much more involved, but the brain script is the CNTK kind of a script way of doing models, which we don't really explain in this slide deck, but that's, yeah. All right, with that, I will hand over to Sayan again. He's going to talk about reinforcement learning.
Right, we are towards the very end of the tutorial. How many of you are familiar with reinforcement learning? All right, not, all right, so we'll go, yeah. So I didn't put much introductory material in the slides, but I have another deck that we will probably soon post as well. So keep an eye for it. What I will do in the next few slides is probably give you a very, very like 50,000 view of RL. It doesn't do justice of introducing the topic, but we will. I'll take a rain check on that and send you guys the slides for a basic deck later on. What I'm going to highlight though is some of you have asked me about Keras backend, that CNTK backend for Keras that got released, and how that can be used for interoperability with other toolkits. So I'll show you an example. How many of you have heard or seen the Flappy Bird game? So there was a nice recipe available on Keras with the TensorFlow trained model, and we were able to use the Keras backend, CNTK backend with Keras with very little. Like I had to comment out 5 references to the TensorFlow code, and it pretty much ran as is. So if you have a Keras code, try it out with the CNTK backend. I'll give you the demo here. Then the other thing I want to get to is in-depth modeling. You have seen a lot of things where we talked about the model using the different layers, library components. We have also shown you some elemental ways of you can access the weights and the biases of a model. Here I'll introduce to you the compute forward and backward passes. There is a tutorial CNTK 203. I actually highly recommend it to my audience here because you're new to the RL. It does cover quite a few things that are very introductory in nature, and it'll help you get a good grasp of what reinforcement learning is about. And then finally, I'll talk about an extensible framework that is in our contrib directory. We take contributions from the community, so if you are interacting with us, whichever ways you would like to, please send us a contribution. This was a very nice contribution that came in. It's one of the unique frameworks that is out there for deep reinforcement learning. I'll give you a brief peek into how you can leverage this framework. I do believe that RL is in its infancy right now, and a lot of the breakthroughs that are going to happen in the next several years to come will build upon the things that are being discussed in this tutorial, from the the convolution nets, and then the recurrence frameworks on top of it, and then go on to the RL frameworks. So key takeaway for the, I think I talked about it, but I'll just reiterate that Keras support, CNTK's Keras support interoperability with the other toolkits. Currently, the CNTK, the Keras supports Theano and TensorFlow, and I heard in the morning session that they are also, Keras is also being supported. MXNet is also a possible backend to Keras. So using this library, we can interoperate between different backend libraries and try out CNTK, especially if you are looking at recurrent networks, you will see an observable improvement in performance. We use low-level APIs for custom RL modeling, so you'll get to see how you can compute the gradients at a very low level for the network, should you choose to do that, and then the extensible framework. So in RL, reinforcement learning, there's an agent that interacts with an environment. It sees a certain state, and it takes an action. And based on the action it takes, a reward is attributed to that action, and a new state is produced. So in the context of a Go game here, you take an action by moving one of these points, and then it produces a new state. Now, the interesting part is you get the reward only at the very end if you win the game. So there has to be a mechanism where you have to attribute your network some amount of gains or some amount of rewards as you go through. In some cases, it might be just for every little transition, it might be zeros, and only if you win the game that you would get rewarded. But the notion of reward at each state can be modeled very effectively. Think about the reinforcement learning agent as a semi-supervised network, where you have certain observable states, and you want to have this reinforcement learning agent learn and predict and perform actions that would lead to that final reward at the very end. So you have very limited observations with the world that you get, and based on the intermediate observed rewards, you can take an action and then keep doing it. And as you do it, you have to start accumulating the rewards. It might be zeros all the way, and then at the end you get one, but there are different ways of attributing these rewards. So here this is the Q-learning is one of the most fundamental ways of training RL agent, and in its kind of high-level form, you start with the initialized state, which is an array of number of states and the number of actions. So the number of states, say in the case of a cart pole game where you're balancing a pole on a cart, it can tip over, and until it tips over, you can say that all those motions of this pole is a state. And these could be discrete states or continuous states. You can model that. In this case, that is the number of that's the different states you observe. And the state space can be quite huge. As you'll see in the Flappy Bird game, that the bird has to navigate through the maze, and that bird can occupy different positions in that maze. So all of those are valid states. Now the bird has to fly through the maze without hitting to the walls of the maze, right? So there are many states, and the actions in the case of Flappy Bird is whether it flaps upwards or downwards. So there's very few actions. But there are other games where you can have many actions. So what I'm trying to get to it is this Q function can be very large, and it would be very sparse. So the whole idea of deep reinforcement learning is how we can model this, how we can approximate this Q table in a more comprehensive way. So let's take a look at it. So what you do is first observe S, And while you're not in the terminated state, that means you have achieved the final state, you would choose an action, given a state S, and receive a reward and a new state, just like I described in the previous slide. Now what you would do is you typically follow a very greedy algorithm. That is, for a given state of your new observed state and the reward and the previous state, you find the action that maximizes the reward for that particular time step. And you take that as the action, the chosen action for that particular step. Now you can imagine that as you are following many steps, the steps that you take now, whether that would be successful many steps later cannot be guaranteed. So you have to give it a discount. So what you do is this gamma is a discounted reward function. It's a parameter of the network where